Okay, so continuing from the definitions, we go into the data reduction. So, for the turning movement counts, this is what the tables from the general counters, the automatic counters used on the outside will look like. So you have the direction, so it should be northbound, southbound, westbound, and eastbound. Under each of these directions, we will have three movements. So we have left, through, and right, left, through, right, left, through, right, left, through, right. Okay, so this is essentially what the data would look like. You have columns. Sorry. Of course, each of the columns have to be populated with numbers starting from 6 a.m. every 50 minutes all the way to 9 p.m. when the count was terminated. So when you go to Miss Wright and you get your data downloaded, you will essentially see a sheet looking like this. This is the basic format of the sheet. You'll see a timestamp over here in a separate column. So depending on the counter, it may be from like this 6, 6:15, 6:30, 6:45, etc. all the way to 9 a.m. And of course, the entire field populated. Now, please note that we are doing a classification count. So the way the software works with the counter is that a sheet will be generated for each, a sheet like this will be generated for each class of vehicle. So for class 1, I'm not too sure what you all use, but the class 1 was cars, class 2 was small maxes, etc. But essentially for the 6 classifications that were undertaken, including pedestrians, you will have these sheets. So you expect to have at least 6 categories per approach or per counter, as the case may be, per session. Right, so these counts are then to be combined, and I'll show you why we combine them later on, because we need to calculate the peak hour. Okay, so this is essentially what it looks like. Now, how do we manipulate this? Well, let me just take one of the rows. Let's see. I use the top row. So let's use some values 25, 75, 15, 0, 50, 25, 5, 100, 10, 0, 50, 0. Recall that I mentioned the peak hour is determined by the sum of 4 consecutive 15-minute periods. But how do we actually compute the total volume across each of these 15-minute periods? Well, you actually sum across the table so that it's not a summation, a vertical summation, it's a horizontal summation. And recall, I just mentioned that you will have approximately 6 categories or 6 classes for the column that you have undertaken. Why is that important? Well, in the case of the volume is computed across all the classes. So you have to combine the 6 classes, excluding the pedestrians, because the pedestrians will be not in the direction of the traffic flow, but they will be perpendicular, as you would have seen in the field. So you sum those tables, and then you sum horizontally. Okay? Now, it may seem counterintuitive initially, but remember from the saturation flow rate computation, the effect of the heavy vehicles and mixing classes is taken care of by the F heavy vehicle factor, that's FHV. So don't worry about the fact that you'll be combining small vehicles with heavy vehicles and so on. That is actually taken care of in another part of the computation. So it's important to remember though, that to work out the peak hour, you must combine all 6 of the tables and then sum horizontally. After you sum horizontally, of course, then you get a summation on this side of the table. So you sum on this side of the table. Okay, so recall previously that we need to combine the tables and then sum horizontally in order to get the sum for the particular 15-minute period. So, jumping ahead, we went ahead and set up the table such a way that we have generated the numbers 320 equals to the 15-minute period. And we use some other dummy numbers just for illustrative purposes. So, once you populate the entire table, we would sum horizontally for all of the 15-minute periods until we get to the end of the peak period or peak study period. For some of you, that would be from 6 to 9, and for others, it would be from 3 to 6. So, the key thing to remember, as in the introductory portion of the video lecture, is that we sum 4 consecutive 15-minute periods. Right? And that, of course, will give us a particular value. Sum another 4 consecutive 15-minute periods, or period, or combination of periods, and we get another value. So this is done until we get we've done for all the periods, and the maximum within that period is taken. Now, from your Excel worksheets, this is a pretty simple computation to make. The maximum value from this column here, I believe, a built-in function of Excel, so you can just determine the max from here. And that is what you do for the particular intersection. Okay, so you work out your peak, then you work out your peak hour factor as described previously, V60 divided by 4 times V15, and then you use that to adjust the volumes on the table. The volume adjustment we will go through in the actual tutorial. It's important just to know how you actually set up the table. So I just use the first few time periods from 6 a.m. to 7 a.m. So 6 to 6:15, 6:15 to 6:30, etc. And then just a basic example to show you how this is actually computed and how we generate the peaks. The peaks. So obviously the first 3 values would not be possible because you have 4 consecutive periods prior. Okay? So it's as simple as that. Okay, so next we go on to the data reduction for the speed study. So you'll recall when we were doing the speed observations, we requested that you, the observer, would be stationed at a particular spot upstream of the intersection. You would pick a spot and you would take recordings of the vehicle speeds at that particular spot consistently throughout the hour, half hour, 50-minute period, as the case may be, that you're taking observations. I would have mentioned to you guys the importance of that because of what we refer to as the cosine effect or the cosine error. Right? Being, of course, it's impossible to actually, or I shouldn't say possible, impractical, to measure speeds of the vehicles straight on. Otherwise, it would be dangerous to be knocked down. Can't stand in the middle of the road, obviously. So we have to stand at some distance away from the roadway or the traveled path of the vehicle. Because of that distance, it creates an angle of incidence at which the radar waves hit the vehicle and return to you, the observer. So that angle, alpha in this case, must be corrected for to ensure that the speeds you actually record are actually what the speeds of the vehicle or what the speed of the respective vehicle is moving at. So with this, you need to ensure that as part of the data collection, you have this distance, you have this distance, the observation point. Okay, so from there, once you have these two distances, you can compute your angle alpha, and then we can make the necessary adjustments to the speed values using the cosine rule. The speed data would have been collected very simply using a basic table. Speed number, observation number and speed. So observation 1, 2, 3, 4, 5, all the way to n, and speed is 50, 55, 62, 49, 37, etc. Sn. Okay? So what do we do? Once we have all of our data, the next step is to actually arrange the speed observations into bins or speed bins. So for example, depending on the spread of the data, we may decide to put the speed into 2 km/h bins, 5 km/h bins, etc. as the case may be. The choice depends on you, the individual or the group, as the case may be. having a look at the observations to determine, exactly what needs to be done in a particular, how the spread of values look, so that we get a nice even chart, which we actually going to discuss in a few. Okay, so the data is sorted. We generate a table from which we'll get the difference of the means, sum of squares, etc. Again, those details I will spare for the actual tutorial. But once the objective of this exercise of the generating the table and speed observations is to generate 3 different types of charts. One is a histogram. Second one is a bell curve or typical speed curve, and the third one is a cumulative distribution curve. All of which you would have done from O-level mathematics, so I expect that you will at least have refreshed your memory with how we actually generate those charts. So, starting with the frequency distribution, we have observed frequency versus speed. And what you would find is that the chart will look something like this. Taking this general pattern. Now, why is this important? Well, readily from the graphic, we can determine what the modal speed is, which is, again, a very important statistic when we're looking at speed data across different facilities and what drivers are actually doing. So the first chart we're going to generate from the data is a frequency distribution chart where we can determine the modal value for our speeds. The second one, not used generate, will be the actual frequency versus speed. And this is typically or generally in the shape of a bell curve or like a normal distribution curve. This chart is particularly important for determining a number of other statistics. One, mean speed, the pace, and some other statistics which we will go through again in the tutorial. Pace, what is pace? Pace is a 10 miles per hour or 16 kilometers per hour band in which the majority of drivers will tend to operate in. So essentially, what we do is we draw a chord parallel to the speed axis that connects both arms of the curve, if I may call them so, and where they intersect, that will be the actual pace at which on a number of vehicles and the pace at which they actually proceed. So it's a range, right? So between, for example, V1 and V2. Now, why is that important? Well, When we're looking at setting speed limits and other safety analyses for roadways of any type, whether it's arterial, freeway, it's important to understand what the general population is actually doing. There is research that suggests that separated apart from the posted speed limit, or the speeds at which a lot of people drive at, it is actually safer if vehicles are mostly traveling at the same speed with little variation between them. So in other words, the more the variation in speed, it is postulated, and in some cases it has been proven, the more the variation in speed, the more likelihood there is to be an accident, or the more likely there is to be an accident, and the less safe the roadway. So that, independent of the actual speed to a point, it is assumed that once you have a majority of vehicles operating within a fairly narrow band, this band being 10 miles per hour, or in our case 16 kilometers per hour, then be safer the roadway. Okay, so this is another statistic you will be required to report on for the coursework. And finally, we have the cumulative frequency curve. So, cumulative frequency. Again, why is cumulative frequency such an important tool in our traffic engineering analysis? Well, in terms of speed, the cumulative frequency essentially tells you at any point along the curve the speed at which a certain percentage of drivers will actually be found to be driving. When we consider traditional means of setting posted speed limits, it is typically done using the 85th percentile speed. That is, the speed at which we would find 85% of the driving population or less driving at. The theory behind that is that the majority of the driving population would set a speed or drive at a speed that is considered reasonable for the ambient or antecedent conditions. So, we are driving along the highway, we see that the road is clear, there are no obstructions, fairly good line of sight, the quality of the asphalt surface is okay. You would find that 85% or less of drivers will not cross a particular speed. So using that logic, engineers, practitioners, policymakers have actually used that as a rule of thumb to set the posted speed limit. Okay, so the corollary to that is that anybody found to be over the 85th percentile speed would tend to be those who would be classed as riskier drivers, risk takers, careless, reckless as the case may be. And the only means to address those would more be in the form of law enforcement. So whether speed guns, enforcement cameras, etc. So that traditionally has been the way speed limits have been set. Recall I mentioned from the bell curve that we use the pace. So in conjunction with the 85th percentile speed, pace has also been used as a measure as well. Sometimes it reinforces what the 85th percentile speed says, sometimes it does not. So in practice, you may actually have a slight difference in the values, and it's up to the policymakers to decide based on other inputs as to what we would like to use to actually set the speed limit. So, for the purposes of our coursework, again, you'll be required to generate the cumulative frequency curve. Again, this is something you would have done from your O-level mathematics or at least A-level, and should be fairly familiar with. If not familiar, at least you would have, gone through some form of cumulative frequency curve computations. We expect that you will recall those in time for the exercise. The 15th percentile speed, this is typically used when actually setting timings for pedestrian crossings. And why do we not use 85th percentile speed for pedestrian crossings? Well, remember, among us, we have differently abled, we have senior citizens and persons who may not be as mobile as they were from some years back. So what we do is that we tend to set the speed for, or the timings for pedestrian crosswalks at the lower end of the curve, so we ensure as best as possible the majority of users can actually traverse an intersection without meeting the green, or without the motorized traffic actually catching the green light and causing injury and or death to the pedestrians. So that is the purpose behind the 15th percentile speed. So these charts, those three charts will be required to generate and provide discussion on the descriptive statistics. So we compute the 85th percentile speed, expect you to understand the theory and the principles behind those, as well as the 15th percentile speed, the mean, median, and modal speed values, the pace. So we expect that by the end of this course, you have a thorough understanding of those concepts. Now, for the final part of the coursework, we are asking you to determine whether there's a difference in the mean speeds for the respective hours that you would have measured. So, again, for example, you would have measured speeds typically from 6 to 7, 7 to 8, and from 8 to 9. Those of you in the morning session. Of course, for those in the afternoon, 3 p.m. to 6 p.m., 3 p.m. to 4 p.m., 4 p.m. to 5 p.m., and 5 p.m. to 6 p.m. Okay. So we're asking you to make a determination as to whether there is a statistically significant difference between the speeds measured, or among the speeds measured between the first period from 6 to 7 and 7 to 8, from 6 to 7, 8 to 9, from 7 to 8 to 8 to 9, and likewise for the afternoon period. Now, what do we mean by statistical significance? Well, if I use my body as an example, if I were to ask the question as to whether this marker is touching my shoulder or touching my body, one would say yes. If I were to ask, again, the same question, whether this marker is touching my body, again, he would say yes. Okay, now, there's a slight difference. The marker was touching left side initially, which is your right now, and it was touching another location at this point. Well, statistical significance works similarly in that there may be slight variations in readings. However, the difference may not be so significant as to make the comment that the speeds are really that different. So really and truly, even though this pen is actually placed at different points on my body, it's still touching my body. If I were to ask you if it's touching my body now, then you would say no. So likewise, when we are in the scientific world, we always refer to the term as statistically significant. And to determine statistical significance or insignificance, there are certain statistical tools that we use to determine whether that is so. So essentially, we go about determining whether there's that difference by computing the means of each or for the speeds for each particular period, etc., etc. And then we compare those means, right, using statistical tools like standard deviation, variance, degrees of freedom, and other appropriate techniques, which again, I don't want to confuse you in this lecture, but as we go through the tutorial, we'll go in detail to see how we actually work this out. Okay? What I'd like to point out is that you should research the student t-test, which is what we'll actually be using to determine whether there is a difference one way or the other. So, student t-test, for which once we compare the means, find the differences, and we generate certain values, then we look up on the particular respective tables and again, this is available, this is publicly available on the web in the manual on transportation engineering studies, which is in the library. And there's a table which gives confidence intervals, degrees of freedom, and certain p-values for the computations that we go through with the differences between the means, which again, as I mentioned, we will actually go into in detail in the tutorial. So needless to say, important point I want you to understand as we close this lecture series is that we require you to determine the difference between the values observed in each analysis period, denoted by respective hours. Once you complete those, we run our statistical analysis, make comparisons with statistical values from the student t-test tables, and make a pronouncement as to whether the speeds are significantly different statistically from one period to the next. And that about wraps up our speed study analysis. Okay, and finally, in terms of the saturation flow rate, most of you would have undertaken the analysis using the Jamar counters. So the output from those counters will give you the saturation flow rates automatically. Some of you were required to undertake the analysis manually. So you would have had your tables in the field, and I would have been on site with you, and you would have been taking recordings using a stopwatch after the fourth vehicle had passed and randomly choosing either the fifth, sixth, seventh, eighth, or ninth vehicle to actually record the time it took to cross the stop bar after the fourth vehicle had actually passed the stop bar. Now, the theory behind that is this. When you have a signalized intersection, and vehicles begin moving after having been at a standstill with the red signal. It takes a certain amount of time for a vehicle to get up to what we call a cruising speed. So vehicle number one moves off, but obviously you do not accelerate and get to your cruising speed instantaneously. So the theory is that after the fourth vehicle, once the fourth vehicle passes, it is assumed that the fifth vehicle would have gotten up to, if not in cruising speed, something closely resembling cruising speed, from which you can actually then assume that the traffic stream is moving uniformly through the intersection, and then you can actually start making your saturation flow rate computations. Recall, saturation flow rate is, by theory, by definition, the maximum number of vehicles that can proceed through the intersection, assuming 1 hour of continuous green time. So the maximum number would also depend on whether the vehicles are moving at steady state or not. So we ought not to be intuitively measuring vehicles that are not moving at the cruising speed. That's why, again, in theory, after the fourth vehicle passes, it is assumed that the vehicles are moving at constant speed or at the desired speed in the traffic stream. Of course, practically that may not happen due to obstacles downstream, etc., but for the most part, that is typically so. So for those of you who did the manual recording on site, you would have had values all over the table, P, A, B, C, etc., etc. So all that we require you to do prior to the tutorial would be to sum the respective columns and have the values listed at the bottom of the table, and we'll discuss how we actually do the computations in the tutorial. If you so desire, you may proceed to Google the methodology for computing the saturation flow rate manually. It's a very simple process. It takes less than 5 minutes, I would say. Once you tally these, you go through the equations, and it's fairly simple. However, if you so desire, we can, during the class period and during the tutorial period, we can go through this in detail so we have a clear understanding of exactly what is required. So, in closing, I'd just like to again reiterate, as I mentioned to most of you on the outside, that the coursework exercise, it's a fairly simple and straightforward exercise. It's not one of the most difficult in terms of complexity of the calculations and so on that are required to complete the coursework. However, it is a lot of work, it's a lot of organization required, it's a fair amount of data, and it will probably have been the first time you would be exposed to such a wide array of data collection activities in one course. So the effort here is really in organizing yourselves early, devising a strategy and a timetable, a schedule, for actually undertaking each of the parts of the coursework. So that is the data reduction, the analysis, and report writing. Please, I would like to implore you, do not wait for the last minute to undertake this. We have seen in the past groups who have waited until the last minute with the best of intentions, and they have not done so well in the coursework. This coursework combined with the pavement analysis gives you a fair jump towards at least passing the course And of course, if you do your work well, you can actually achieve a lot more. It's a course that everybody can get an A or an A plus, as the case may be. So I just want to implore you to make sure and take the time and effort to get the data early. Ask your questions. I'm available. I will leave my email contact with Ms. Wright, and we will have it when we get to class. And to really get a good handle on the project so that you can ace this course. So with that, I'll just try to close off, and I wish you all the best in the course, in the coursework. Please feel free to ask as many questions as you like. That's what we're here for, to clarify and to make sure you understand. I look forward to meeting you during the class time and the tutorials. Thank you.